Okay, good morning. Let's see. So yesterday we spent a lot of time talking about metric fair algorithms, but in case you forget the definition, remember that the goal is that similar people should have similar probability distributions on outcomes. So we have a metric, and we need that the distribution on outcomes for individuals x and y has distance at most, or difference at most, to d of xy. Okay. So remember that I sort of started off yesterday by saying that for at least quite some time, the bulk of the research on algorithmic fairness had sort of split into group fairness and individual fairness. And one of the problems with group fairness criteria was that natural group fairness criteria were mutually exclusive, and we saw an example of that. So this, of course, renews interest in individual fairness. And so here's the question: does individual fairness actually resolve that problem? Of course not. Nothing can resolve that problem. That's just a mathematical statement. Good. Okay, so if any of you how many of you have worked in the software industry? Quite a few, okay. So you know that systems are composed of lots and lots of different parts. And clearly anybody who's responsible for any given part should wish that their particular part will be fair. And the question is, if you have a system that is made up of individually fair parts, is it going to be the case that the system as a whole is fair, or has some kind of at least natural degradation? Maybe it'll be a little bit worse according to how many different parts are being assembled. So that's the goal that we have is for this, and the intuition might be that this should be the case, but it's much more complicated than that. Sorry. All right, so let's give a kind of surprising example of why this is the case. Think about when you surf to, say, the New York Times. Hold on a second. Something's in my throat. I'm not sick. So think about when you surf to the New York Times. There's a banner ad. You might have a couple of ads, but let's just simplify it and assume that there's a single banner ad. What actually happens before that banner ad is shown to you? Anybody know? There's actually an auction that happens really fast in the background. So different people who are tracking you and watching you and know various different things about you will decide on an amount to bid for your attention. And so there's very, very fast, there's an auction that happens, and this slot is sold off, and you are shown an ad. So imagine the following scenario. We have two advertisers, very simple. And one of them is advertising a tech job, some kind of high-tech programming job, something like that. And the other one is advertising a grocery delivery service. Now, grocery delivery services are sticky. Once you get a grocery delivery service, you're likely to repeat or stay with it. So it's pretty valuable. Does anybody know who really, really wants grocery delivery services? Let's forget about the pandemic, because many of us are living on them now, but pre-pandemic, who wants those? Yeah. New parents, that's right. Okay, so grocery delivery service, new parents need it, it's sticky, so those guys will bid a lot for your attention. If they know that you're a new parent, how might they know that you're a new parent? And you've probably all read the articles in the paper. Okay. So, great, so what happens? Well, the grocery delivery service wants your attention now. You're a new parent. They want your attention right now, and they're willing to pay a lot for it. The tech jobs advertising, they want you, but they always want you. And they don't particularly want you more now that you're a new parent. But, forget about that. They whatever. So what will happen in a scenario like this is that the grocery delivery service will offer a lot of money for your attention. And the tech jobs ad, completely ignoring the fact that you're a parent, but the generic tech jobs ad is not going to be offering as much. So that means new parent sees the ad for the grocery delivery service. So you could almost think about it as if the grocery delivery service is just getting first dibs. Because it's paying more, it's just getting first dibs. And then whether or not somebody even has the chance of seeing the tech job ad depends on whether they are in the leftovers after the grocery delivery service has made its decision. So you could almost imagine that these things are ordered sequentially. They're not. It's an auction and it happens, but in terms of priority, this is the effect. All right, so, all right, so there, we named this kind of composition competitive composition because these two advertisers are competing. And the key point here is that the tech jobs advertiser should not touch with a 10-foot pole whether or not you are a new parent. And they don't. They may be doing absolutely everything they're supposed to do. And yet the effect in terms of whether the new parent sees the tech jobs ad is biased. Any questions on this scenario? Okay, and it's real. This is real. And I was at, I don't know, some conference or other, and someone at Google who was very high up in charge of the ad platform was speaking, and I asked about this, and he completely shut me down. He said, what the advertisers do, the advertisers do. We have no role, we have no responsibility. Well, that's not so clear to me that they have no responsibility. Okay. So in general, as that example shows, competitive composition is not guaranteed to be fair. And in fact, we can prove a more general result, which says, suppose we have two different tasks. Think advertising tasks. So one task might be the grocery delivery advertising thing, and the other task might be the tech job advertising process. And suppose the metrics for these two tasks are just D and D prime, and they are non-trivial. So we're going to say that a metric is trivial if all of the distances that it assigns are either 0 or 1. I mean, it can be a mix of zeros and ones, but those are the only choices. And it's non-trivial if there's some stuff in between. Okay? So, and let's assume that there is a tie-breaking function. In the case of the advertising, the tie-breaking function was money, greater than money, right? So, but it could be an arbitrary tie-breaking function. It doesn't have to be the same for each individual. Then there exists classifiers, C for task T, and task T is governed by metric D, and C prime for task T prime, which is governed by metric D prime, so that C and C prime are individually fair for their respective tasks and distances in isolation, but if you combine them naively, then you will get a violation of sort of the fairness of the system as a whole. Was that a question?
Yeah, for the definition of a trivial metric,
Yeah.
is it that the distances are either 0 or 1, or are they in the interval?
Oh, those are curly braces, so set.
Set.
Either
Okay.
zeros or ones,
Okay.
yeah. Mm-hmm. Any other questions? Okay. Okay. So that's a theorem. Any questions on the theorem? So we're going to sketch the proof of this theorem. And we're going to sketch it for the special case in which whenever there is a tie, the preference goes to task T. All right. Now, so what are we going to do? Because the metrics are non-trivial, let's look at metric D. I'm going to assume that there are points U and V, or individuals U and V, that the classifier assigns probabilities PU and PV to such that PV is greater than PU, and that's strictly greater than 0. Okay, and then I'm going to assume that C prime gives, assigns probabilities P prime V and P prime U to U and V, V and U respectively. And the only requirement is that PU prime is at least as large as PV prime, and PV prime is non-zero. And moreover, we're going to require that the distance that between PV prime and PU prime is maxed out for the fairness guarantee, which means that the difference between them is the distance metric D prime on UV. Okay. So these are the things that we're going to need, and we can do this based on the non-triviality assumptions. Okay, so I want to think about the system as a whole. So we have these two tasks, and I want to see what is happening to somebody, an individual U or an individual V. Which ad do they see, or if any, do they see? Okay. So remember that task T has preference. It wins whenever there's a tie. So if an individual U sees the ad that's given by T prime, task T prime, that means that they were rejected by T. It wasn't that they both, that both T and T prime classifiers bid on them. So they're, or one. So they were rejected by T, and they got to T prime. So the probability of that is 1 minus PU times PU prime. And now for V, the same thing. It's 1 minus PV. It has to be rejected by T. So when we drew from the distribution given by classifier C, the outcome, that gives a distribution for V, and we draw from that, and the outcome was 0. So that's this part. And then it got a positive outcome when we applied the C prime classifier. Okay? So manipulation shows that this is just the distance under D prime between U and V, plus these cross terms in red. PV times PV prime minus PU times PU prime. So now let's do a case analysis. Suppose that PU is actually equal to PV. And remember, these are maxed out. That would mean that the distance between U and V is in fact 0, which is allowable. So if that happens, then we're done. Oh, by the way, so we're going to have a violation of fairness when the probability of a positive outcome in this combined system for seeing the ad that corresponds to T prime, when that exceeds the distance metric between U and V under D prime. So that means that this stuff in red has to be positive. Whenever that stuff in red is positive, we have a violation. Questions? Okay. So now, again, if the distance between these is 0, then this term is 0. And what happens? It says because this distance is 0, it must be the case that, can you see? You cannot see my cursor. I forgot. Let me get you a pointer that you can see. Okay. Good. So because D prime and UV is 0, then it has to be that PU prime is equal to PV prime. So coming back up here, PU prime is equal to PV prime. So the red term is positive whenever PV minus PU is positive, and that is what we have by assumption. Okay? So now, what happens if the distance between U prime, D prime between U and V is not 0? So now we're just going to do a little bit of manipulation. We're going to let alpha be PV over PU. So the red stuff here can be re-expressed as alpha times PU times PV prime minus PU prime. So this stuff now is greater than 0 whenever, dividing through by PU, which is non-zero by assumption, alpha times PV prime minus PU prime is greater than 0. And now, doing a little bit of manipulation, that's going to be true whenever PV over PU is greater than PU prime over PV prime. But we have some flexibility here, and we can, as long as we don't disturb the distance, the overall distance, as long as we don't exceed this distance, we can move PU and PV around. We can shift them over to the left towards 0. Even if they're maxed out, we can still shift them together towards 0. And so here's PU sitting around in the denominator. It's the smaller of the two. As it gets to 0, this ratio is growing. And we can push it as close to 0 as we want in order to, as we need in order to get this violation. Now, so that's kind of the idea of the proof. And there are some details that I've omitted, which is U and V are not the only two elements. And so when I move them around, I'm going to have to move other people around sort of with them in order not to exceed the Lipschitz constraints for the other individuals. But that's not very difficult, and we can do that. So that's what I wanted to say about this result. Is there a question? Any questions? So, yes? Not hearing yet.
Are there any other motivations other than advertisement for such a...
Oh, what a great question. Are there motivations for competitive fairness other than advertising? Sure. Different firms hiring. Different schools trying to either get students or hire somebody. Anytime that there is real competition between two different agents, you can probably come up with a scenario that looks something like this. Good. Excellent. More? Okay. So is there a solution? Let's look at the advertising problem. Is there any solution? Can you think of any solution that would combine individually fair advertising classifiers to get something that's fair in total? Yeah?
Some of the problem seems to be with ordering. So can we randomize the order and try to ensure that ordering doesn't give an advantage?
Excellent, you're on the right track. The suggestion is, can we randomize the order? Of course, there really wasn't an order because the grocery store was outbidding the others. I sort of said you could think about it as an order, but you're definitely on the right track. And in fact, we call the system randomize then classify. So the idea is, look at all of the people who are bidding or competing, whatever the scenario is. Put a probability distribution on those. Choose a task, because I'm not caring about being fair to the advertisers in this solution. I don't care how it's actually, what probability distribution I place. But put a probability distribution of the tasks, choose any task according to this distribution, and now classify using a fair classifier for that task. So this is pretty straightforward. Think about it later. Why would an advertising platform hate this? Yeah?
You're not like maximizing profit, I guess.
Right, you're leaving money on the table. Yeah. So is there anything that can be done about it? There are some, at least one, maybe two papers in the literature I know of that deal with relaxing the fairness constraints in ways that you might or might not decide are reasonable. I mean, you as the reader have to read it and see what you think, and then you can do a much better in terms of revenue. Yeah. But often, because of our definitions of fairness, there are trivial fair solutions. And this one is not trivial, it actually does something, but it's just kind of a starting point. You want better utility maybe from it. Okay, so if you're sort of used to thinking about computing, you might imagine a different kind of composition. So, ors and ands. Right? So, an example of or fairness, sorry, is what happens when an individual applies to multiple colleges. Now, when you think about the college situation, yes, an individual might definitely prefer college 1 to college 2. Different people may have different preferences, or they may agree on their preferences. But fundamentally, what matters when a student is applying to college is that the student be accepted somewhere, that they get into college. And the exact set of which acceptances and rejections they had, while it feels very personal and meaningful, may be much less meaningful. So let's say then that the relevant outcome is to get into at least one college. And let's say for simplicity that the different colleges are all using the same metric D, which of course is not necessarily the case. So then we would say a set of classifiers, C for task T, that have a shared metric D, satisfy or fairness if for every U and V in the universe, the probability that U gets into at least one college minus the probability that V gets into at least one college in absolute value is bounded by the distance between U and V. Okay, that just says the chance that each of them gets into, all right. So we're sort of redefining what is the goal, and the goal is the or, getting into at least one. Now, let's suppose that we have these two students, and let's suppose that they're not assigned probabilities of 0. That is to say, the chance for each of them that the chance that they get into at least one school is non-zero. Clearly, if they apply to enough schools, they're very, very, very likely to get in somewhere. Okay? So you can imagine that with enough levels of composition, things will, we know that with enough levels of composition, things will converge to 1. And the funny thing is, like, it doesn't stay nice and together the whole time. So if PU and PV, that is the probability that U gets into at least 1, and the probability that V gets into at least 1, if both of those are less than a half, and we look at what happens under actual realistic numbers of composition, somewhere, 5, 6, 7 schools, they actually can diverge quite a bit before coming together later on. So it is the case that for any non-trivial task, there's a set of classifiers that are fair in isolation, but that violate or fairness. That's what this gap is under certain numbers of composition. Interestingly, and then this is kind of immediate, you characterize when you just look at the chances of failure and you see what happens as the number of colleges that are applied to increases. Okay. If for each of the different classifiers by the different schools, if for each of these and for each person in the universe, the probability of a positive classification is greater than a half, then that gap doesn't manifest and things work nicely. So that says that you can kind of something happened with my picture. There we go. You can rethink this a little bit. You could take a bunch of different classifiers, you can pull them together and say, if I bunch a few of these together, is it the case, if it wasn't the case that for every U, C1 assigns a probability of at least a half, can I bunch a few of them together so that for every U, this collection has together a probability of at least a half? And if we do that kind of clumping, now we're in the situation where we can apply this result because we'll have like these ore of heavy ores. Each of these is taken as a collection, has probability more than a half for each individual. And there's nothing special now about the fact that these CIs that we're combining them using an OR. Whatever it is, whatever these functions are that are going on in these blocks, whenever these things can be amalgamated in a way so that together their probabilities for everybody is at least a half, you can pull them together and get OR fairness that way. What about AND fairness? I have 2 ringers here at least. Chelsea, Sylvia, any comments on AND fairness? No? You had this as a homework assignment last semester. Okay, so AND fairness is complicated. And it's not even clear what it is we actually want, especially when we start thinking about having different metrics. So this is a good thought exercise. What would be the right definition for AND fairness? What would you hope for? What can you not do? What can you do? Yes? Can't hear yet.
Are you assuming all colleges have a shared applicant pool?
Ah, very good. Very good. Good. So in the example, I was assuming that, or I was using that. You can tailor things to the actual situation and then see what makes sense. This was just done as an example. Good question. Yeah. And I think that the reason that we chose it as an example is that it was a situation where really all that mattered was the OR. I mean, we could convince ourselves that the most important thing was the OR and not the actual set of acceptances and rejections, and that there was no reason to assume or to require that similar people should have similar distributions on sets of acceptances and rejections. And it's kind of presented in the spirit of, like, you know, you're the designer. You get to choose what matters and what it is you feel needs to be made fair. Yeah. Okay. All right, so the next set of results are on dependent classifications. So far, we've been thinking of things as if all the decisions are made independently. But that's not what actually happens. If you're a bank, you don't necessarily have even the resources to approve all of the qualified loan applications. If you're a university, you might only want to give out a certain number of acceptance letters. You might have further constraints, like maybe you require that at least half of your students are able to pay their own way, because otherwise you can't cover the operating expenses of your school. Or you might be trying to field soccer teams for men and for women. And so you need a certain number of soccer players but not too many. So there are two main settings here. One is where there are dependencies, but we don't necessarily have a fixed sized requirement. And in particular, you can have situations where certain people show up. I think I've got a question about something wrong? What? Is that better? Okay. So you have to deal with the fact that, let's say you're a private school, you're a public school, and you have to figure out where to place the various students. And it's a school district where there's some kind of choice among which schools you get to go to. And you're not necessarily working with all of the students in the district. It might be that some of the students were diverted to private schools. So, and then you have to think about, like, well, how did that diversion happen, and what is the fairness requirements that you need? Are they only for the people who actually are here, or do you need fairness also with respect to people who didn't show up? The other is the cohort selection, where you're trying to accept a set of a certain size, and now you have size limits. Okay. So, in fact, there are a lot of different axes. So, for example, you might be doing things like deciding whom to interview, or what set of people to interview, or what set of people to hire for a team. You might be doing this in an online fashion, or you might be doing it in a batch fashion, right? We've already discussed whether you're operating on the universe as a whole or whether you're operating on the subset of the universe. And then there are differences. If it's in the online case, do you know in advance the number of people who are going to show up? Do you know the size of your universe? Do you know the size of your subset that you're going to have to deal with? If you don't know the size, you have much harder decision making. It's much more fraught. Okay. If it's in the online case, is the ordering in which people are appearing or your decisions are being made adversarial, or is it random, for example? And again, the case where you have to make sure that at least half the people that you admit can pay for the school or have some skill for your band or your orchestra or whatever. Okay. So I'm going to focus for a moment on the cohort selection problem. So we're given, again, our universe of individuals, U, and an integer, n, and we want to select n individuals from U so that we maintain individual fairness. And again, the point is, up till now we've been talking about completely independent classifications, and now we can't. So here's a negative result. This is our constrained cohort selection, again, where we want to admit n students, and at least half of them have to be able to pay full tuition. An alternative would be that you need to satisfy statistical parity for legal or moral reasons. Or, again, the soccer teams. Great. Okay, so here's a simple special case. My applicants are split into two groups, A and B. And the split is according to economic means. The people in A can pay. The people in B can't pay full tuition. And it turns out in this example, in this contrived example, that the size of A, and it doesn't really have to be this way, I'm making it extreme for simplicity. The size of A is exactly n over 2, exactly the number of people you need to admit who can pay the full tuition. And I'm going to make the size of B k times larger for some constant k bigger than 1. And we're going to assume, or in this example, B is like a blown up version of A. So for every individual here in A, there are k people in B who are at distance 0 from this person in A. So there are k copies, so to speak, in terms, yeah. Not copies exactly, but k people who are distance 0 from this guy, k people who are distance 0 from this guy, and so on. Now, because we need n over 2 people who can pay their own way, everybody in A has to be admitted. So if U is in A, then the probability of acceptance for U is 1. And now, by a pigeonhole argument, we know that there's somebody in B whose probability of being accepted, admitted, is less than 1 over k. Because we can only take 1 over k of them because we only have n over 2 seats left, and there are k times n over 2 people in B. So let's say this top green person has P sub v less than 1 over k. All right, so now this is a huge problem. This one's probability is less than 1 over k. This one's probability is 1, but the distance between them is 0. It's a complete and total violation of the Lipschitz condition. It's not really shocking. It's just an argument that when you have the constrained situation, things are much, much harder. And they can be impossible. So I'm just going to say a little bit about kind of the most general formulation of this. This slide is actually packing 2 definitions into one. So the stuff in green is when we're talking about cohort selection, which means taking a group of size n. And when we don't have the green stuff, it's just a selection problem. So we take an approach here that's like modeled on indistinguishability in cryptography. And remember that we have to deal with the fact that who it is who shows up to apply or interested in the school or whatever, that that's governed in some sense by rules that we can't control. We might know them, but we can't control them. So, accordingly, we're going to let Y be a distribution over subsets of the universe. Then we're going to have a distribution on permutation, for every V, which is a subset of the universe, I have a distribution of permutations on the elements of V. So why am I talking about distributions? I'm talking about distributions in part for the online case. And the online case may not be so relevant in school admissions, but it might be very, very relevant in in hiring, because there are people who know people on the inside who are going to sort of show up first, and then because they heard about the job opening and they kind of have the jump on everybody else. Okay. So we have distribution on permutations of the elements, and for a system S that maps permutations on subsets of the universe together with randomness to, now, in the universe subset problem, it's just some subset of elements of U, or some elements in U. In the cohort selection problem, this is a set of size n. So this would be U super n instead of U star. So with those definitions, we define an experiment where the number n here is, it exists when I'm talking about cohort selection because then I want a set of size n, and otherwise I just want an arbitrary set. So we're going to choose a random string. We're going to choose a subset of elements of the universe according to this distribution. We're going to choose a permutation randomly according to this distribution. And then we're going to run the system that takes a list of people with randomness and outputs a set. So this experiment, when I'm running it with individual U, is going to output a 1 if U is selected by this whole big procedure, and 0 otherwise. And now we can actually talk about comparing the probabilities that U and V get selected in this system. So we have a language for talking about it. We haven't specified exactly what's fair and not fair yet, so we need to do that. And we say that the system is individually fair and potentially a solution to the cohort selection problem. If the probability, the difference in probabilities here is controlled by the Lipschitz constraint, bounded by the distance between U and V. And for the cohort selection problem, this is a set of size n. So this is the goal that we have for cohort selection. The easiest setting is a basic offline cohort selection. Decisions are made offline with access to the entire universe U and with access to the metric D. And you have no constraints on the output set other than its size. So since you know what U is, you know how many candidates there are. And then there were two mind-bogglingly difficult, conceptually easy, mind-bogglingly difficult in practice solutions to this. So in permute, then classify, we choose a random permutation on the set of all, we choose a random permutation on all of the elements in U. So we choose a random ordering. And then we classify each element as usual using a fair classifier until either we found n elements and then we stop, or we don't have n elements yet, but there are exactly enough people left that you haven't marched through yet, so that if you put all of them in, you would have a cohort of size n. And then that's the end condition. You dump all of them in. Okay? So that turns out to be fair, individually fair. And the proof is more or less as you would expect. You get a lot of power out of the fact that the initial ordering is random. There's a little bit of work in arguing that things go right at the end condition. And a different solution is called weighted sampling, where you can enumerate all sets of size n, and for each one of them, you assign a weight, which you eventually have to normalize, but it is proportional to, for each set T, you look at how many people you expect overall are going to be accepted among the sum of the probabilities that each of these U's in T is going to be accepted. And so that gives you an ordering and then, weights. And once you have the weights, you can normalize and choose from that distribution. So you're more likely to choose a set that has more people who have high C values. Okay. So those two, as I said, they're complicated and they work, but these basic ideas have shown up in the subsequent works that I mentioned that try to look at relaxations of individual fairness and and increase revenue. So these ideas are sort of fundamental. Okay. Any questions on these? Yeah.
Isn't it quite expensive to enumerate all sets of size n?
Isn't it expensive?
Yeah.
Do you remember when I said mind-bogglingly?
Oh, okay.
Okay, yes. It is. But if somehow or other you could do something with some small set of things and have that generalized, then it's useful. So there are cases where these ideas have come into practice. Come into algorithms. Okay, I want to mention one final flavor of composition. We're not going to talk about solutions here, but I want you to be aware of this problem because it's a real problem, and the machinery that I know of is heavy-handed, and it would be great to have something that was much lighter. So imagine that you have a company. The company hires a team to do something or other. And then at some later point, bonuses are meted out to people in the team, or maybe somebody in the team gets promoted. So there's like a stage 1, which is the formation, and stage 2, which is some other activity, which often will depend on some kind of score, performance-based. So hire a cohort, 1 year later, promote a cohort member to team leader. We'll take that as our running example. Notice that whether or not you in particular get promoted may depend on your cohort. The other thing is that the scenario that we're interested in is not a completely crazy scenario. Like, the issue that we're going to be dealing with is how the interaction between the first stage and the second stage. And if you have the same person who is doing both of these activities, then maybe they can sort of plan for the future when they do the team hirings or whatever, to take various fairness considerations into account. But a lot of times that's not going to be the scenario. And it's going to be somebody completely different who is making the decisions 1 or 2 years later than who made the hiring decision initially, the team formation decision initially. So when you start thinking about this problem, you can come up with whole new catalogs of evils. And yeah, I encourage you to do so. We have some. So the general problem is 2-stage cohort pipeline, universe U, a permissible set of cohorts. And you have some kind of cohort selection mechanism that maps the universe, your candidates probably, to a cohort. And I'm going to call that the hiring manager. And then applied much later is a collection of scoring functions, big F. Each function, I abused notation here, each function is mapping the cohort together with an individual to a score. So scoring, as I've said, is contextual. How well you do might be viewed in relation to the other members of your team. Of course, it's not just straight comparison. You have to, like, in reality, things are, how well you do may depend synergistically on the people in your team. It's not just straight competition. But there's just some function that takes the cohort and an individual and comes up with a number between 0 and 1. And there is no requirement that if I look at 2 different cohorts that could contain individual U, that the score that U receives would be the same in each of these cohorts. That's, again, this point. Your score may depend on your cohort. And we're going to say that F of CU is just undefined if U is not in the cohort C. And that C should be a lowercase c. So our pipeline, oh, did I get it backwards? The pipeline is apply A and then apply F to the result. Okay, so we're going to let C sub U denote the set of cohorts in our collection of cohorts that contain individual U. And you know, there can be constraints, like when the hiring is done, it might mean you might need one person who's an expert on front end, blah, 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 and somebody else who's an expert on back end, blah, blah, blah. You can have different sort of skill sets that are captured in these different cohorts. And we're going to let the probability that A selects individual U be denoted by P of U, and it's the sum over all of the cohorts that contain, possible cohorts that contain U, of the probability that that cohort was selected. And we're only going to be interested in cases where the scoring function is fair, at least within a cohort. So if U and V are both in the same cohort C, then the scoring function, F of CU minus F of CV, that difference should be bounded by the distance between U and V. So informally, there's a very sort of simple fairness definition, which requires that for every function in our collection of scoring functions, the pipeline that's instantiated with that function is individually fair with respect to the similarity metric D and the distribution metric, which evaluates similarity between distributions on the outcomes of the pipeline operation. So the distribution metric takes two different distributions on the outcomes of the pipeline, maps it to a number, and the requirement is that for all U and V, these differences, the distance between these two distributions should be bounded by the metric distance. Okay. Any questions so far? Yes. Ooh.
Don't the cohorts change from different stages in the pipeline? Like,
Can you say that again? What change?
won't the cohorts change from different stages in the pipeline? Like at the hiring process, some people don't get hired.
Right.
And so that's a different cohort comparison than when I'm promoting.
Right. So the function f, so the question that's raised is, sorry, the cohort is the set of people who are hired. Let's assume that it's stable and those people are all there the following year. All right? Let's just assume that for now, because I'm just looking at a simple two-stage pipeline. Does that answer your first question?
Yes.
Okay. Another question?
And there is an assumption that there's no blank slate condition. Like often, I guess, we're not assuming that when you join the job, we sort of forget of how you got the job and we're only comparing how you did at the time that I've hired you. We're saying it also mattered how or why you got hired.
So you're asking, so the fact that, sorry. The function that maps cohort comma person in that cohort to a score may or may not care about how they got hired. We haven't constrained that function. Right, yes?
I think it's related to that question. You are assuming that D does not depend on the cohort. So even after...
Which, sorry, the distance between U and V does not...
individuals.
Right.
But actually after the cohort is hired, maybe the relevant distances to make the decision about the promotion are different than the ones that, so it's a different task. It should have a different metric.
So this is a good point, and the way I'm thinking about it, now that you have raised this point, the way I think about it is that I have a metric for the pipeline itself, the effects of hiring and scoring together. So I'm not assuming that the same metric is used at hiring time as at promotion time. Okay? I think that's right. Do you want? Let me think. Maybe I am and maybe I shouldn't be. Let me think about it. Thank you. Other questions? This is a good one. Okay. So I'm actually going to say very little about this after the definition. All right, so this is our notion of fairness. And if the pipeline is individually fair with respect to this metric and this distance, then, and for every function in our class, then we say it is robust to the function, to this class of functions. So the key point here is that somehow or other, the hiring manager and the promoting manager can't probably operate completely independently. Or if they are going to operate completely independently, the hiring behavior might be very different from what it would be if there's some policy that governs how promoting happens. And that kind of communication is essential. So our hitch, of course, in all of this is that the outcome space involves the fact that some people don't get hired. So in general, in a pipeline, individuals drop out voluntarily or involuntarily, and you have to talk about what does fairness mean in this case. I'm not going to give you the answer to this. I'm going to tell you that there's some machinery set up for thinking about it for any particular context you might have. So our starting point is that the first phase can have either bottom if somebody isn't hired, or it could have or it could hire people. So we're going to let psi u be an element in this distribution that places a probability 1 minus the probability of hiring on bottom, that's not getting hired. And it will place a certain probability on every possible score S between 0 and 1, which is given by the probability that if we apply a function f on the cohort individual pair, we get a score S, times the probability that A output this particular cohort, which is one of the ones that contains U. So it places that probability on the number 0, 1. So some probability on bottom, the not hiring probability on bottom, and the scoring probabilities, the probabilities for each score otherwise. And then you have to think about, like, what's the right distribution? You want to take these and you want to map them to numbers between 0 and 1. Instead of having a distribution on bottom and union 0, 1, you want to have a distribution on just 0, 1. So we start from here, but then we're going to treat bottom as having a score of 0. That's called the unconditional distribution. And the conditional distribution only works with the probability, it kind of ignores the probability of not hiring, and it reweights the probabilities of scores conditioned on being hired. So this seems like a really reasonable thing to do, because in some intuitive sense, you might think you only care about this. And then you get weird situations like this. So suppose U and V are pretty close. Their distance is 0.1. And suppose that under A, they're hired with the same probability, so no fairness problem here. But suppose also that A never chooses, A is free to do whatever it wants. It never chooses a cohort that contains both of them. So they each have the same probability of getting hired, but they'll never be hired together. Okay. And now we suppose that we want to constrain F for the unconditional distribution. So we're looking at the probability of U times F of U minus the probability of V times F of V, and we want that to be less than D of UV. This is now going to simplify because P of U and P of V are the same. It's going to simplify to some P star times F of U minus F of V. That has to be less than D of UV. And if P star is small, that's a very weak fairness requirement. And if you allow this, you can end up with situations that look like this. Congratulations, you've been offered a job. After a year, you may expect a promotion with some probability, F of U for U or F of V for V. Same probability of getting hired, but in this example, U for Olfar and V for Virginia receive very different looking offers. They could have very different hiring, they could have very different scores later. And that difference is just completely mitigated by their small probability of being hired in the first place. So this satisfies some kind of notion of fairness, but clearly they should perceive these offers very, very differently. And that's the kind of thing that we have to deal with. So with that, I'm going to stop with composition, and we'll talk about affirmative action after the break.